Good morning. That looks like it's just you, Savannah. Good morning. Can you hear me?
Yes, we can hear you.
Thank you, Ali. All right, folks, it's 9:30. We'll get started. So today we're going to be looking at Hess's Law, which has to do with combining equations in order to find heats of reaction or enthalpies. So the situation we're dealing with is one very much like what you would deal with when combining simultaneous equations or solving for simultaneous equations, systems of equations, if you will. I don't know if any has, I'm sure a lot of you have done those kinds of things before in math. This is kind of similar to that. So let's talk about what the situation is with this Hess law. So often, or a lot of the time, we can't figure out the heat of reaction because it's not practical to actually put the reactants together. I suppose it would be in this instance, but in some instances it isn't possible to put two reactants together and get the product we want. We actually have to figure out what the heat of reaction is based upon other reactions that could be combined to give the reaction that we actually want. So this is the situation we have here. We're looking for the heat of reaction of N2 plus O2 gives 2NO. Now we don't actually have the delta H for that. So what we're doing here is we're using two reactions that we do have a delta H for, and that's this one here, half N2 plus 1 O2 gives 1 NO2, 2 NO plus 1 O2 gives 2 NO2. And we have these delta H values here as well. So the idea here is we want to manipulate the two equations so that when they're added together, they come out to the one that's in the question. So what can we do? Well, we can do two things. We can flip the reaction. Now, if we do that, we reverse the sign on the delta H. What I mean by that is positive goes to negative and negative goes to positive. All right, so let me give you an example of how that works. Let's say we've got a reaction where A is giving B, and it has a certain energy profile. And it looks like this. So energy, reaction pathway. And we're going from A to B. You can see that the delta H would be the difference between the two. So the delta H is going to be B minus A. And I know that this is going to be a negative value because B is smaller than A. So that's going to be negative. Is everybody okay with that? Does anybody have any questions so far? All right, let's say I reverse this reaction. I make it B going to A. What I would want you to see is now B is the reactant and A is the product. The delta H is still going to be now A minus B, but because A is bigger than B, it's going to be a positive value. So that's what I mean. If you flip the reaction, then what happens is you change the sign of the delta H. If it was negative, it becomes positive. If it was positive, it becomes negative. Does anybody have any questions so far? Okay. The other thing that we can do is if we multiply the reaction, then we multiply the delta H. Now this one's fairly easy to explain. I'll give you an example. Let's say you have a gallon of gasoline and you burn it. It's going to release a certain amount of heat. I don't think it's too much of a stretch to say that if you burned 100 gallons of gasoline, you get 100 times the heat. So it's pretty much the same thing as that. So you multiply a reaction, you multiply the delta H as well. All right, so those are the two rules that we're kind of looking at. Flipping the reaction flips the sign of the delta H, multiplying the reaction multiplies the delta H. Any questions so far? Right, so let's see how we deal with something like this one. Remembering that we need the delta H for this specific reaction. So what we do is we look at the reactions that we've been given, and you can see I've rewritten them up here. And you look to see if the things in the reactions you have are on the correct side. Now, what I mean by that is we're looking at N2. N2 only appears in this reaction that we're looking at here, number 1. And you can see the N2 is indeed on the same side as we need it to be in the reaction that we're looking for. So what that would tell me is that this reaction does not need to be flipped. So if it's on the same side, the side it needs to be on, then you don't need to flip the reaction. Now keep in mind this only applies to compounds that appear in only one of the equations you're given. I can't say the same thing about oxygen here because O2 appears in both of these equations, so I can't really use that as a guide. N2 I can certainly look at because N2 only appears in this equation. It's on the correct side, so equation 1 does not need to be flipped. Now looking at the NO though, NO appears in the second equation, but you'll notice it's on the wrong side. So what I'm going to need to do is flip this entire reaction. And by flip, I mean the reactants become the products and the products become the reactants. So the 2NO2 goes over onto the reactant side and the 2NO plus O2 goes onto the product side. The other thing I do here is I change the sign of the delta H from positive to negative. All right, I'm going to stop there for a second. Does anybody have any questions about what I've done and why I've done it? So once you've got everything on the correct side, and you're only dealing with the things that appear in only one equation. I hope you understand what I mean by that. So N2 and NO I can look at. O2 I can't really deal with because it appears in both equations. I'll say that again. O2 I can't deal with because it appears in both equations. So I go through that, and then the next thing I do is I want to make sure the coefficients match. So in the equation I have for the N2, I've got half N2, but in the equation I want, I've got 1 N2. So what that means is I'm going to have to multiply this reaction by 2. So I do that. I get 1 N2, 2 O2, and 2 NO2. And the other thing I do is I multiply the delta H that I have by 2. So 33.2 becomes 66.4. Does anybody have any questions? All right, so these are the modifications we made just in summary. All right, we flipped 1. And we flipped 2, I shouldn't say flip 1, flipped 2. We flipped 2 and we multiplied reaction 1 by 2. That's what we did. So these are the equations that we've come up with at this point in order to get to the situation that we're in. You'll notice that the NO has the correct coefficient on it, so I don't have to do anything else with that. So that's good. All right, so we've got 2NO2 gives 2NO plus O2. One thing I think is a good idea is try to keep the arrows above each other. And that way you don't get confused about what's on what side. So these are the two reactions we have that we've modified. So 1N2 plus 2O2 gives 2NO2. And that one's going to be 66.4. So that's what we've done so far. Now I'm going to stop here for a second. Does anybody have any questions so far? Now the hope is that once I've done that, I've flipped what needs to be flipped, I've multiplied what needs to be multiplied, that magically when I add these together, I will come up with the equation that I want to come up with. So let's see if that happens or not. You'll notice that on each side of the arrow, remember these are reaction equations. They're called equations for a reason. It's almost like the arrow can be treated like an equal sign, which means if you've got things on opposite side of the equal sign that are the same, we can get rid of them. So we can get rid of the 2NO2s. Now the N2s, that's all we have there, but we do have 2 O2s on this side and 1 O2 on this side. So what I can do there is subtract O2 from both sides, and I'm left with 1 O2 down here. And look what happens here. We get 1 N2 plus 1 O2 gives 2 NO. And then we can add these delta H values together. That's negative 114.1, sorry. Then we can add these delta H values together, and that will give me the delta H for the reaction that I wanted, which is going to be negative 47.7. When we're looking at the significant figures, it's going to be based upon addition, subtraction. So it's going to be number of places past the decimal, which means this is going to come out to be 1 place past the decimal, negative 47.7. All right, so that's my introduction into this. Does anybody have any questions?
So when you're adding, so you're not necessarily adding them up like system of equation, you're canceling out, so you treat them each as like individual um, factors of the equation, basically.
Well, I'd say it's very much like systems of equations because you do a lot of cancelling with that as well.
Oh
You know,
yeah, but
if you've got x's and y's, you've got two equations with x's and y's. The idea is to cancel out one of the variables so you can find one of the variables, right?
mm-hmm.
Yeah, this is not overly different to that. It's a little bit different, but we're taking similar approaches because in systems of equations, you do exactly this kind of situation. You flip equations and you multiply them in order to make sure things cancel, right?
So if they're on the same side, you would subtract them basically, I guess.
Now, if they're on the same side, you would add them together.
Okay, okay, that makes sense.
Like if you had, let's say you had 202 and 102 down here, then that would be 302 in the final equation.
Mm-hmm.
But when they're on opposite sides of the arrow, that's when you subtract because it's like they're like terms.
Okay, that's kind of what I was. Okay, that makes sense.
All right. So what I want to spend time on now was just some examples. Now the examples we're looking at are in the Hess Law folder, and I had this document here called Hess Law Problems. And we're going to do some of these. Now these have the answers here as well. So these are good for practice too. Now I'd like to look at, let's say, I'm going to go ahead and expand this a little bit here. If I can find the, there we go. All right. Yeah, so we'll look at number 24 here. That's an interesting one. It's a little bit more difficult than some of the others, but we'll get through it. So here is this one has 3 reactions in it, and we're looking for this 4th reaction down here. Now, one thing I can tell you is that generally speaking, we can pretty much ignore the states. When I say states, I'm talking about gas, liquid, solid, etc. The only time you can't really do that is when you've got a compound that has, let's say it was H2O liquid and H2O gas. So if you have one compound that has 2 different states, you probably couldn't ignore the states then. But in this kind of situation where everything in the reaction only has one state, then we can just go ahead and ignore the gases and liquids. So it makes it a little bit easier for us. We don't have to take into account so much here. So I'm not going to rewrite this problem here. Can everybody see the problem? Number 24?
Yeah.
Okay. Just want to make sure it's big enough for everybody to see. So we've got, this is the one we're looking for. HCl plus F2 gives 2HF plus Cl2. That's our aim. And here's what I want you to realize is that if you do everything I told you to do, if you make sure everything's on the correct side, you make sure everything has the correct coefficient, then magically, when you add everything together, it will come out to the reaction you want. I guarantee it. You have to have that faith that that will work out. So looking at the HCl, for example, so what I do is I kind of look at the reaction, and I'm just looking for where things are. So HCl is here, and HCl only appears in one equation, it appears here. And you'll notice that it's on the correct side. The issue, though, is that in the equation we want, it's 2HCl, but in the equation we have, it's 4HCl. So the remedy for that would be to, since it is on the correct side, and I know it is, I just need to divide the first reaction by 2. Is everybody okay with why I'm doing that? Okay, so I'm going to go ahead and write that out. 2HCl plus 1/2 O2, and then H2O, and Cl2. So do you see what I did there? I just divided all of the coefficients. 4 by 2, 1 by 2, 2 by 2, and 2 by 2. And additionally, I take the delta H and I will divide that by 2. So that would be negative 74.2. All right, does anybody have any questions about what I'm doing so far? All right, next I look at the F2. I see I have F2 here. Looks like the F2 is on the correct side, so that's good. So I've got 1/2 F2 here. And I'm going to take number 2, and I'm also going to divide that by 2. And that's going to give me, no, I'm not going to divide it by 2, am I? What am I going to do? What should I do, folks? What should I do with number 2? Dividing it by 2 is not going to be the answer. Anybody know? Nobody knows?
I'm thinking you gotta flip it, probably.
No, you don't have to flip it because the F2 is on the correct side. So remember, this is the reaction we want. The F2 is on the left side, and up here the F2 is on the left side. So that's okay. What's the problem though?
It's yeah.
Does anybody know what we have to do with number 2?
It's not divide.
Nobody knows, huh? Well, I'm not sure. Either nobody knows, has any clue, or nobody's actually at their computer. They're just, but I'm not really sure. I don't know.
Well, I guess I'm trying to look at both of these, and it's kind of I'm trying to go back and forth and try to see the difference, because I see 2 HCl plus 1/2 O2 H2OCl, right? And then I'm looking down here and I'm seeing H2O2 H2O. Oh, but we're doing 25, aren't we?
We're doing 24.
Oh, then I don't.
We're doing 24. Look, there's 17 people logged in here, or supposedly logged in. And you're telling me that there's nobody here who knows what to do with equation 2 in order to make it so the F2 matches what we have here. Is that what I'm understanding?
I'm having a little hard time reading it. It's 1/2 F2 in that second equation.
If you're having trouble reading it, you should have told me. I would have enlarged it. It's easy. All right.
Okay. So then all you need to do is multiply by 2, right?
Yeah, that's right.
Okay.
That's all you have to do is just multiply by 2. That's all I was looking for. I wasn't asking too much.
Well, I guess what was throwing me off is like there was a CL in the top, and then I guess there was no CL in the bottom one.
Doesn't matter. See, well, look, here's what we're doing. We're focusing first of all on the HCl. So that's why in the first reaction, this is 2 HCl, this is 4 HCl. So I divided the first one by 2 in order to make the HCl's match. Okay. Then I went down here, I looked for the F2. F2 is in this equation. It's only in the second equation. It's on the correct side, but we need to take this half and get rid of that. So we multiply the whole thing by 2. And we're going to get H2 plus F2 gives 2HF.
Oh, so you're trying to get all parts of the element, like you're trying to get all the different parts down to the last equation. So
yes,
you're dividing, subtracting, or whatever to try to get as much as you can down there. Okay, I got you.
That's right.
Can you use these equations more than once?
Well, yes, as many times as you need to, but understand that if you've already determined that something's on the correct side, then you absolutely cannot flip that equation. And once you've flipped it once to get it on the correct side, you can't flip it again.
Because it cancels out.
Right.
Okay, so you can only do one thing just one time of time.
Really, you can either multiply once or you can flip once.
It's about your only thing. Okay.
Yeah, that's all you can do.
And so basically, realistically, you can only do 4 things and add them together.
Mm-hmm. In this case, yeah.
Yeah.
All right. Okay, so that's what we had to do for that. Does anybody have any questions so far? Now, if looking at you see we've already taken account of the HF, which was in the second equation, the CL2, which was in the first equation. You'll notice the third equation actually doesn't contain anything that's in the final equation here. But what I would want you to see here is that if you were to use the third equation as it is, then nothing in there would cancel out. We know that everything in here has to cancel because it's not in the final equation. So what I'm going to have to do is I'm going to have to flip the third one to make it cancel. So if I flip the third one, here's what I'm going to end up with. H2O gives half O2 plus H2. And that means we flip that to be 285.8. Positive 285.8. Does anybody have any questions?
I have a question.
Yeah. Mm-hmm.
So I missed like the first 10 minutes of this. And when I'm looking at this, you're doing these equations and you end up with a number. How do you get that number? Is there like an equation?
No, you just add them all together. Like I'll take
add the molecular weight?
No, I'll take these delta H's that I have over here, David, and I'll add them all together.
Oh, yeah, that's what I'm asking about. How do you get the delta H's?
Well, they're given.
They are? Okay.
Yeah, they're given. See?
Right.
But we do different things to these reactions, and that changes the value of the delta H's. So flipping the reaction changes the sign, and multiplying or dividing the reaction multiplies or divides the delta H. See,
Okay.
when I took the first equation, I divided it by 2. It divided the delta H by 2. Do you see that?
Yeah, no, I get it. That makes sense.
Okay. So once I've done that, and you'll see now why I had to flip number 3, the half O2s can cancel. The H2s cancel.
How are you feeling?
And the H2Os cancel. So if I hadn't have flipped number 3, I wouldn't have been able to get all that stuff to cancel. And when this stuff does cancel, we end up getting...
Well, she wants you to see if you've got strep throat.
We end up getting the equation we want. And then we add up all these values here. And we get a value, which I'm going to see if I can find in a second. Oops. Sorry. I hit the wrong scroll bar, and now I'm having trouble getting back to the tab because this Zoom thing keeps on popping back. Here we go. Oh dear. No, it's not going to let me do that. Hang on. Here is a scroll bar. That's what I'm looking for. Okay. And that should give us negative 988.4 as our answer.
So is it pretty standard for these problems that you're gonna have through reactions?
Well, sometimes you'll have 3, sometimes you'll have 2.
Okay, but it's not anything crazy like we're gonna have like 5 at one point?
No, you could possibly have 4, but that would be the limit. But generally 2 or 3.
Okay. Thank you.
And you know, this is the thing. You just got to have faith that if you do the right, if you flip everything you need to flip, you multiply everything you need to multiply, that it will add together to give what you want. And just make sure you do what you need to do to the delta h's as you go. All right. Does anybody have any questions?
Yeah, I have a question.
Mm-hmm.
So when you're doing the equation and you're dividing and multiplying,
Mm-hmm.
what are you doing that for? Are you doing it to eliminate the the spectator ions, the
Well,
things that don't?
well, I wouldn't call them spectators, but what we're trying to do is we're trying to find a delta H for a reaction we don't have the delta H for. But we're doing it by manipulating reactions we do have the delta H for. That's all. That's all.
So in the first equation, how do you eliminate 1/2 O and H2O? Is that by dividing by 2? And if that is how you do it, then how does that work? It doesn't seem like that would eliminate it.
No, it doesn't. See, the thing is, you've got to focus on, look at the equation you want, right? It says find the delta H of reaction for this equation. This is the equation we want, the one. You can see my cursor, right?
Yeah.
Yeah. So you focus on the things you have in this equation, the one you want. So you look at the HCl. So you find HCl. Oh, it's up here. It's only in one equation, so that's important as well. If it's in, if what you want is in 2 equations, I would ignore it because you can't really do much with it. But if HCl only appears in one equation, and it does, then you can see it's, first of all, you determine 2 things. Is it on the correct side? And does it have the right coefficient? So looking at this, it is on the correct side. And you'll see that this is a 4, but this is a 2. So that's why we took the first one and divided it by 2.
Okay, that makes sense. But the second one doesn't make sense because you multiply it by 2, but you already have 2HF on the what would it be called, the reactant side or
No, because if you look here, I've got half F2 in the equation, the second equation.
Oh, okay.
And I've got F2 in the equation I want. And it just so happens that when I do multiply this by 2, I end up with 2HF, which is what I wanted anyway.
Okay, that makes sense. I just didn't see 1/2 in your equation that you wrote down. I was looking at that. Anyways, thanks for explaining that. I get it.
Okay. Now, the hard part, though, is this third equation, which doesn't contain anything that's in the final equation, but knowing that you have to flip that. Now, you won't always have to flip it, but in this case, we had to, because otherwise, if we didn't, then nothing here would cancel and we wouldn't end up with the equation we wanted. All right, that's the hard part. Does anybody have any questions?
How does flipping it eliminate all of those things on the final equation?
What's that, sorry?
How does flipping it eliminate H2O, 1/2 O2, and H2?
Because if you have the H2O here on this side, I'm just going to put check mark next to it. We have the H2O over here. You'll notice they're on opposite sides of the arrow, right? So when we add them together, they cancel out.
Okay.
The arrows are just like an equal sign. Think of it like that. And if you've got opposite things on opposite side of the equal sign that are the same, then we can cancel them, right?
Okay. So you just kind of look at it like an algebra equation.
Yeah, it's like systems of equations, David.
All right.
Have you done systems of equations before? Simultaneous equations?
I wouldn't remember stuff like that by name.
Oh, okay. I don't know. I think it's something you cover in college algebra, but I'm not 100% sure.
I guess what confused me the first time when you did that was like, oh, I never seen that cancel out trick, and it makes sense because if you just add them all up and then like you just move one to the other side by subtracting it from the other side, it's the same effect.
Yeah.
Yeah. It's just that you sort of like you did it in a way that I'd never seen before, and that's why I got confused the first time.
Oh, okay. Is anybody, is anybody else concerned or has any confusion about this whole cancelling thing? I mean, it's kind of important.
It makes sense. It's just a little, like, the concept is a little weird.
I guess I'm trying to couch it as an algebra problem, really, Emily.
Yeah, thinking about it that way, it makes sense.
So, I mean, have you all seen stuff like this? 2x plus y gives 40 and...
Yes, I've seen stuff like this, and the thing that causes me confusion is that I've never done that canceling trick before. I usually just add them up and then I subtract from the other side. I never thought to do it this way, but since you showed this to me, now I can use it in a different equation as well. It's just I've never seen this trick before. That's why I got confused. It's
Well,
not
I
the
don't like to
concept.
think. I don't like to think of it as a trick. Oh gosh, because
Well,
it's not a trick. Good Lord.
Well, it's just a different way of approaching it. It's a new tool in my tool belt to say,
Oh,
hey, I
right.
can solve it this
All
way.
right.
Is that a better way to look at it?
Yeah, let's look at it that way.
Okay.
All right. Anybody got any questions? Okay. I know you've all seen systems of equations before. I know you have. And if anybody tells me, oh no, I've never seen that in my life, then I know you're lying, because I know that you cover it in pre-algebra or college algebra, one of those two. I just know it. I know it. All right, I'll look at number 26. This one's a little bit simpler. Probably should have done this one first, but we'll do number 26. So what we're looking for here is 2SO3 gives 2SO2 plus O2. That's what we want. So again, you know, I like to look at the reaction. We've got SO3 down here. SO3, as you can see, is over here, and it's on the wrong side. So what that tells me is I'm going to have to flip number 2. I'm going to do it down here, keep it as number 2. So flip number 2, and if I do that, then it becomes SO3 gives S plus 3 halves O2. And that would be positive 395.7. And if we look at the SO2, the SO2 is on the incorrect side as well. Oh, and additionally, there's one other thing we have to worry about too. Notice that the SO3 in what we want has a 2 in front of it as well. So what I'm going to do is I'm going to flip 2 and I'm going to multiply it by 2 as well. So we'll do 2SO3 gives 2S, and then that'll be 3O2. And then this will be 395.7 times 2. So it'd be 791.4. All right, so I've pretty much done all I can with equation 2. Now I look at the SO2, I see the same situation. It's on the wrong, so it's on the correct side. It is on the correct side, so I don't have to flip it. But the 2, does need to be multiplied by 2. So I'm going to take reaction 1 multiplied by 2. And that would be 2S plus 2O2 gives 2SO2. And again, I will multiply. And I get 593.6, still be negative though, negative 593.6. So you'll notice after I've done all that and I add all these together, you'll see that the 2S's cancel. And here we've got 2 O2s and 3 O2s. So that's going to be the 1 O2 over here. So it will be 2SO3 gives 2SO2 plus O2. Then I add the delta H's together. And I get 197.8 kilojoules per mole. All right, does anybody have any questions? Anybody have any questions?
Why did you multiply the first one by 2?
Because if you look at the reaction we have, the one we're looking for, notice there's a 2 in front of the SO3, but up here there's nothing in front of the SO3, there's a 1.
Mm-hmm.
So I have to multiply the second equation by 2 in order to put a 2 in front of the SO3.
Okay.
Are you okay with why I had to flip it as well?
Yes.
Okay. All right, any other questions? So that's all we're doing. We're just flipping and multiplying the reactions in order to get what we want at the end. And that should be able to get us to where we need to be. All right, so what I'd like to do is go through, let's see. Now this is in the Hess Law folder, this problem sheet. As I said, the answers are there as well. Let's take a look at the Hess Law practice quiz. This is for extra credit, if you'll remember. And now I also have a link here to some Hess Law problems. This is kind of cool. You hit new problem and it comes up with the equations, and then you have to figure it out. And then in the answers, it tells you what it did, what it flipped and what it multiplied. So that's good practice too. So that link is in the Hess Law folder, and there's a whole bunch of problems there too. You just keep on clicking on new problem, will come up with new problems for you, and it'll tell you if it's right. So that's a good resource as well. All right, so this is the Hess Law practice quiz that we're going through. Now, some of this covers some of the stuff that we've already done with the enthalpies as well. So for example, for number 1 here, what it's looking for is the formation reaction. So remember we dealt with heats of formation the other day. This is an application of that. So for something like this one, this is it. This is on the Hess Law practice quiz. We're looking for HGO, and it's the heat of formation. Now, if you remember what I had said about heat of formation, the definition of it was the energy released or gained when a product or a compound is made from its elements in their natural states. Okay, from their elements in their natural states. I'll go ahead and write that down. We did this the other day. All right, heat of formation. Equals energy released or gained when a compound, it's important, the word there is compound. Compound is not an element. When a compound is made from its elements in their natural state. So what you're looking at here is HGO. Does anybody want to guess at what elements are used to make HGO?
Mercury and oxygen.
Yeah, Hg and O. Now, the only thing we have to be concerned about here, though, is it does say, this is important, they're natural states. Now, we talked about this the other day as well. If we look at the tables, and you have access to these tables, this is in the test 3 folder, I think in the enthalpy folder. Anything that's got a 0 next to it is an element in its natural state. So all we have to do is find mercury, which will be under M for mercury. There it is. And I look for the form of mercury that has a 0 as its delta H of formation. Because look, I mean, think about it. If you've got an element in its natural state, that is the basic form of that element. And you don't need any energy to form something like that. So it's going to be Hg liquid. And then oxygen in its natural state, we can do the same thing. Just looking for O, see oxygen, where is oxygen? There it is. And it's O2 gas. So you don't even have to know that, you can actually just look it up on the table. Now these are kilojoules per mole. But another way of looking at that is kilojoules per 1 mole, which means this has to keep a 1 in front of it. If I'm looking for the heat of formation of HGO, which I can get again off the table as well, mercury, here you go, negative 80.3. So this, you've got to understand, would be the energy that would be released when we add mercury and oxygen together, but this is not balanced. In order to make this balanced and keep this 1 in front, because the 1 has to be for 1 mole, then this would be 1/2 and this will be 1/2. And that's it. I know we don't usually do that. We don't usually put coefficients in that are fractions, but in this case we have no choice because we need the heat, the delta H of formation, and the delta H of formation is 1 mole, it's kilojoules per 1 mole. So that 1 has to stay there, we can't multiply it out. If we did, then we'd be doubling it. Does anybody have any questions?
So you have to keep it in terms of 1.
That's right.
Always.
Yes, because of what we're asked for.
Okay.
Where we are asked for the heat of formation, delta HF naught, which we get off the table, which you're pulling off the table, but it's in the units of kilojoule per 1 mole. So the reaction has to reflect that as well.
And that little circle is just at standard.
Yes, that's right, standard conditions, which is what the table is measured at, which is why, which is specifically why we end up getting that.
So we're only looking up for, when we're looking at the table, we're usually only looking for the reactant side or the product side.
Well, at the end, yes, you're only looking for the products because it's a heat of formation of a compound.
Mm-hmm.
The heats of formation of these is always 0.
Exactly. Okay, I got you. So you can't really put 0 and 0 and get 90.83.
Right, and that's not the point. The point is that if I take these two and put them together, that's how much energy gets released.
Gotcha. And you can do that just by like making the bonds and then seeing how much it is between them and adding them up. But like you said, but you gave us this table to say like, hey, this is what it is of this specific element. Okay.
That's right.
Okay, that makes sense.
That's all you're doing, you're just pulling it directly off the table. But knowing that these have to be in their natural states, which are always going to be a 0 next to them.
I see. So since O2 is its natural, O is its natural state, it's single element, so that's why you have to cut it in half.
Well, no, O2 gas is the natural state. The half is because there's only one O in the product.
Oh, I see what you're saying. Okay.
Oh, and actually, now I'm looking at it, I don't need a half in front of the HG. I'm sorry about that.
Okay.
I don't need that. Sorry about that. I did need a half in front of the O2, but I don't need one in front of the HG. You're right.
That makes a lot more sense. I was a little.
Yeah.
Yeah. So sorry, Emily. That was my error.
What number did you put in front of the HGL in that box? It looks like
Okay.
it's 1 or 9.
It's a 1.
Okay, it's a 1. All right. And then what's in that little bracket directly underneath it to the right? Looks like negative 908 with a square bracket at the end.
Oh, no, it's 98, negative 90.83
Negative
kilojoules.
90.83 kilojoules.
Yeah, this was what was pulled off the tape. See this here?
Okay. Yeah, I see it.
Okay. Sorry, I shouldn't have put the half in front of the mercury. That was bad. All right, does anybody have any questions? Okay. Question 2. Now, what it's asking here is, it's a multiple choice. It's a flip equation 1, flip equation 2, flip equation 1 and 2, flip neither equation 1 nor equation 2. So this is actually fairly easy, because what we're looking for here is we're looking for equation 3, and you know that because the delta H has all these question marks next to it. So what we do is we look at equation 1 and we look at equation 3, C10H8, and that appears in equation 1 and doesn't appear in equation 2. So you can see that I don't have to flip equation 1. And O2 I can't really look at because O2 appears in both equations, so I can't really look at that. CO2 I can look at though. CO2 is on the incorrect side. So I can see that I wouldn't flip equation 1, but I would flip equation 2. So the answer there would be flip equation 2 only. Does anybody have any questions? So you can see that the value in this quiz is because it kind of goes through and piecemeal. It tells you can figure out what needs to be flipped, what doesn't need to be flipped. Now this one is about multiplying equations. So again, we do the same thing. So we look at the C10H8, it's got a 1 in front of it, and you can see it's got a 1 in front of it here in the final equation. So we know we don't have to do anything with the C10H8. And the CO2, it looks like that doesn't need to be multiplied. It's got a 10 and a 10 on it. So in this one would be multiply neither equation. We wouldn't have to multiply either of them. Right, does anybody have any questions? Then in this last question here, you actually have to figure out the delta H. So you'd put it all together. I think the catch though in the credit quiz is that they're all different reactions. I mean, they're all different problems. So you're not going to get the same thing going for each of them. In the practice quiz you do, but not in this one. So that's the basis of what you're doing in the practice quiz. I think it's really useful. It's extra credit, so I think you should do it.
So that practice quiz, it still has an unlimited number of attempts, so you can take it as much as you want to study, and it's extra credit?
Well, the practice quiz, you get 80%, and that opens the credit quiz, but you get 2 attempts at. That's what's extra credit.
Oh, okay. Okay.
Now, the purpose of the practice quiz is just to give you an idea of the formatting and what the credit quiz looks like.
Okay. That makes sense.
And to practice the formatting, essentially. And then you know exactly what you're going to see, and then you can do but obviously you've got to make sure you understand what you're doing first before you do the credit quiz, because you only get 2 attempts at it.
Yeah.
And the other advice I would have, if you bomb the first attempt, get help before you take the second attempt. All right. Any other questions?
Yeah. For enthalpy, what would you recommend me to look at to sort of understand it? Because I don't really have a basic understanding of how to do those problems on the practice quiz.
Well, what I would do on the practice quiz, you're talking about in here?
Yeah, in the module as a whole for enthalpy.
Well, I'd watch the videos, and I'd go back and watch the lecture that I put up 2 days ago.
Okay.
I think you had made the comment that you weren't able to pay attention to the lecture because you were having computer problems or something on Monday.
Yeah.
So I'd watch that lecture.
Okay.
And then I would also go and watch these, not these videos here in the mini lectures folder, especially heat and work, enthalpy from delta H of formation. That's the one you should focus on, and estimating delta H by bond energies. Those two, you should watch those.
Yeah. Okay.
And then when you're taking the practice test, I do have videos for those actual problems that relate to that. So you should look at those too.
Okay.
And that, if you still don't understand it, then you should talk to me.
All right.
But I think after doing all that, you'll be sick of it and you'll know.
Yeah.
All right, we're going to look at the practice test. I want to show you the kinds of problems that relate to Hess's law on the practice test. And again, I have videos for these problems too. So you'll see it's not that bad. Here we go. This is it here, question 3. So here's an example. Obviously, you get different ones every time you take it. But the more often you take it, eventually you'll probably see all the examples anyway at some point. Let's see. Numbers change though. So that's not overly helpful at times, but we'll see. Okay. So here is this is what you'll have to do on the test when you practice test when you take it. You'll notice they're not real compounds, right? There's just A's, B's, and C's and things. Now, I know it looks a little different to what we've seen, but I do have videos that explain how to do this as well. So this is what we're looking for. A gives C plus F. So we do the same thing as we've been doing. So I look for A. I see it's in equation 1. I also notice it's on the correct side and it has the correct coefficient. So that tells me that I'm not going to do anything to equation 1 at all. I look at C and I see that C is only in equation 1 and it's on the correct side. So that's good. And again, it's got the right coefficient, so I don't have to do anything with that either. But F, on the other hand, is on the wrong side. You can see that it's here in the product, but here it's in the reactant side. So I know I am going to have to flip that. So equation 1 I'm going to leave as is because I know I can, or I know I must actually. Now you shouldn't do this in your head. You should write it down, obviously. And I'm going to change equation 2 here. I'm going to flip it. So flip 2, and it's going to be G gives F, which means that's going to be negative 16 now. And then we've got G gives 2B plus D. You'll notice this is one of those situations now where we've got things that are not in the final equation. So you know that those things are going to have to cancel. And you can see in this instance that if we left the G on the same side here as it is here when we flipped it, that they won't cancel. So I know I am going to have to flip number 3 as well. And that will give me D gives G plus 2B. I know they're not real compounds, but it's not any more difficult or any less difficult than what we've been doing, I don't think. In fact, I think it might be even a little bit easier. So it'd be negative 187. So we do that, and you can see that because we flipped it at the end, the G's cancel, the two B's cancel, the D's cancel, and all we're left with is A gives C plus F, which is what we wanted. And then, of course, we take these delta H values, we add them all together, and that gives us our answer. Does anybody have any questions? So again, that's what's on the test. I'm being completely transparent here. You do that, and you do those questions continually. You'll understand how to do them. You'll be fine.
As far as like pace of all these things go, do you recommend that we do like 3 of the sections a week?
Well, no, what I'd recommend is that we cover stuff in lecture, and then in the days like from when, let's say you don't do anything on Tuesday, that's okay, right? But from Wednesday through Sunday, that's when you cover the things we did on Monday and Wednesday.
So just stay on pace with you and we should be fine.
Absolutely. It's always, that's all I've ever wanted. It's all I've ever wanted.
I just know that some sections are more in depth than others. So I didn't know if you, and I should give you more credit. You probably will be pacing them at that rate as well.
Well, the things, look, we've covered enthalpy, bond energy, and Hess's law.
Mm-hmm.
And over the next 5 days, I'm expecting people will review that stuff. They'll do the practice quizzes, the credit quizzes, and then they'll go in, they'll take a look at it on the practice test and master it there as well. How long will that take?
Easy.
Probably about maybe 3 hours is what I'm thinking. 3, maybe 4 hours. I've pointed this out to people. I sent out an email. Not everybody got this email, by the way. Only certain people did. But what I had pointed out was that a 3 ECH course requires 6 hours of revision and study per week. And that's how I've paced the course. Just using the SPC credit hour guidelines. Now, if you don't like the credit hour guidelines, that's fine. I don't really care if you like them or don't like them. They are what they are. And that's how I've set up the course in accordance with that. You might think they're unreasonable. You might think that 6 hours per week for a subject is too much to have to study. And my response is, I don't give a crap. I don't give a crap if you think that's too much time. I'm just following the rules. I'm just following what I have to do. To be blunt, that's what I'm doing. And by the way, it's what every other instructor and professor does as well, if they're a good instructor. It's up to you to meet the challenge. All right, any other questions? Because that's pretty much all I had wanted to cover today was the Hess's law, and go through all the different resources, which I did. So everything you need is in the Hess law folder. All right, does anybody have any questions? Okay. All right, if anybody wants to hang around and ask me anything, you're more than welcome to. Otherwise, I'll see you all later.
Sure. Thank you, Professor.
Thank you.
Yeah.
Have a good day.
Thanks, David. You good, Chloe?
Sorry, I had you on not full screen, so now I'm trying to get it's not going back on full screen. There we go.
Oh yeah. Oh no.
Yeah, there we go. Okay, yeah, I had you on like half screen, so I wasn't able to put it back on full screen to leave. Thank you.
Okay, no worries. Thomas, can I help you? All right.